Okay, so something genuinely strange is happening at the edge of the observable universe, and nobody, and I mean nobody, fully understands it yet. When the James Webb Space Telescope started sending back its first deep field images, scientists were already bracing themselves for surprises. Webb was always going to be revolutionary. That was the whole point. It was designed to peer further back in time than any telescope before it, to catch the first light that ever flickered on in the cosmos, to help us understand how galaxies formed, how stars ignited, how the universe went from a hot, featureless soup of particles to the staggeringly complex structure we see today. So, yes, surprises were expected, but nobody expected this. Scattered across Webb's deep field images, these impossibly sharp photographs of regions of sky so small they'd be covered by a grain of sand held at arm's length. There are these little objects, tiny, compact, almost easy to miss if you're not looking for them. But once you see them, you can't unsee them. They glow with this deep, almost burnt reddish hue, sitting there against the black of space like tiny embers. Astronomers started calling them little red dots, and that nickname, casual as it sounds, has stuck in the scientific literature because frankly it describes them perfectly. And the thing is, we don't know what they are. That's not hyperbole. That's not the kind of "we don't fully understand this yet" that gets thrown around loosely in science communication. This is a genuine, active, ongoing, scientific mystery that has some of the world's most respected astrophysicists scratching their heads, rerunning their models, and in some cases seriously questioning whether our foundational understanding of how the early universe worked might need to be revised, possibly significantly revised. These little red dots appear to exist at extraordinary distances. We're talking about light that has been travelling toward us for over 13 billion years. They seem to be impossibly massive for how early in the universe's history they exist. They seem to be putting out extraordinary amounts of energy from incredibly compact regions of space, and they show spectral signatures that don't quite match anything we were expecting to find. So today we're going to dig into all of it. We're going to talk about what these objects actually look like in the data, why they're so confusing, what the leading hypotheses are for what they might be, and what the implications are if any of those hypotheses turn out to be correct, because some of those implications are genuinely universe-altering. But first, to understand why these red dots are so shocking, you need to understand what we were supposed to find out there. Chapter 1. What we thought. The early universe looked like. Let's set the scene. The universe is approximately 13.8 billion years old. We know this with remarkable precision, thanks to measurements of the cosmic microwave background, the faint afterglow of radiation left over from the early universe, combined with observations of how fast galaxies are moving away from us, and a whole suite of other cosmological tools. 13.8 billion years, that's the age of everything. Now, in the very beginning, and we're talking fractions of a second after the Big Bang, the universe was unimaginably hot and dense, a kind of primordial plasma where matter and energy were effectively indistinguishable. There were no atoms, no molecules, certainly no stars or galaxies, just a seething, expanding fog of fundamental particles. As the universe expanded, it cooled. After about 380,000 years, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms, an event cosmologists call recombination. Before this moment, the universe was opaque. Photons couldn't travel freely because they kept colliding with free electrons. After recombination, the universe became transparent for the first time. Those photons streamed out freely, and they've been travelling ever since. We see them today as the cosmic microwave background. But here's the thing, after recombination, the universe entered what's called the cosmic dark ages. There were no stars yet, no galaxies, just vast clouds of neutral hydrogen and helium gas, slowly being pulled together by gravity. The universe was dark, cold, and relatively uniform. If you could somehow be there, you'd see nothing, absolute darkness in every direction. Then, sometime in the first few 100 million years after the Big Bang, the first stars began to form. These were not stars like our Sun. They were enormous, potentially hundreds of times more massive, and they burned hot and fast, living violent, brief lives before exploding as supernovae. They're called population 3 stars, and we haven't directly observed any yet, though Webb is trying. As these first stars and the first primitive galaxies began to form, their ultraviolet radiation started ionizing the surrounding hydrogen gas, essentially stripping electrons from atoms again. This process is called reionization, and it gradually transformed the universe from a foggy sea of neutral hydrogen into the more transparent, ionized state we see today. Reionization is thought to have largely completed by about 1 billion years after the Big Bang. Now, within this framework, which is called the Lambda Cold Dark Matter Model, or Lambda CDM, and represents the current standard model of cosmology, there are very specific predictions about what galaxies should look like in the early universe. They should be small, they should be young, they should be irregular and messy, because they haven't had time to grow and settle into the elegant spiral and elliptical forms we see in the nearby universe. They should have relatively low masses because mass accumulates over time through mergers and star formation. And the supermassive black holes that sit at the centres of galaxies, which power some of the most energetic phenomena in the cosmos, should also be in their early stages smaller and less energetic than the monsters we see in nearby older galaxies. This was the picture, tidy, logical, well supported by decades of theory and observation. Webb was sent to test this picture, to observe these early, primitive galaxies directly for the first time in proper detail, and almost immediately the picture started showing cracks. Chapter 2: The Telescope That Changed Everything. Before we get to the red dots themselves, it's worth taking a moment to understand why Webb is capable of seeing things that no telescope before it could see. Because the engineering here is genuinely extraordinary, and it's directly relevant to why these discoveries are happening now rather than 20 years ago. The Hubble Space Telescope, launched in 1990, was a revolutionary instrument. Its deep field images, the Hubble Deep Field, the Hubble Ultra Deep Field, were iconic. They showed us that even a tiny patch of apparently empty sky was packed with thousands of galaxies, each containing hundreds of billions of stars. Hubble changed our perception of the scale and richness of the universe, but Hubble has limitations. It primarily operates in visible and ultraviolet light. And here's the problem. The universe is expanding. Objects that are very far away are moving away from us very rapidly, and this causes their light to be stretched, shifted toward a longer wavelengths. This is called redshift. The further away something is, the more its light gets redshifted. By the time we're talking about objects at the distances we're discussing, galaxies from the first few 100 million years of the universe's history, their light has been stretched so dramatically that what started out as ultraviolet and visible light has been shifted all the way into the infrared. Hubble can't see infrared light effectively, so those earliest galaxies were largely invisible to it. Webb was designed from the ground up to see in the infrared. Its primary mirror, that gorgeous gold hexagonal array, is 6.5 meters in diameter compared to Hubble's 2.4 meters. That's not just a cosmetic difference. The light collecting area of a telescope scales with a square of the diameter, which means Webb collects roughly 7 times more light than Hubble. Combined with its infrared sensitivity and its extraordinarily precise instruments, Webb can detect objects that are fainter, further away, and more redshifted than anything Hubble could see. And then there's where it sits. Webb orbits at what's called the second Lagrange point, or L2, a gravitationally stable point about 1.5 million kilometers from Earth, on the far side from the Sun. It's shielded from the heat and light of the Sun, Earth, and Moon by a 5-layer sun shield the size of a tennis court. This keeps Webb's instruments at extraordinarily cold temperatures, close to negative 233 degrees Celsius, which is essential for detecting faint infrared signals, because at those wavelengths, heat from the telescope itself would otherwise overwhelm the signals from distant objects. The result is an instrument of almost incomprehensible sensitivity. Webb can detect the heat signature of a bumblebee at the distance of the Moon. In terms of its ability to see faint, distant, infrared bright objects in the early universe, it represents a quantum leap beyond everything that came before. And so, when scientists started analysing Webb's first deep field images, they were looking at patches of the early universe that had literally never been seen before in this kind of detail. Every pixel was potentially a discovery. Every faint smudge of light was telling a story that no instrument had ever been able to read. That's the context in which the little red dots appeared. Chapter 3: The Discovery. first glimpses of something wrong. The first systematic reports of these strange compact reddish objects started appearing in scientific preprints in 2023, roughly a year after Webb began science operations. Astronomers were poring over data from Webb's various deep field surveys, programs like CEERS, the Cosmic Evolution Early Release Science Survey, and JADES, the JWST Advanced Deep Extragalactic Survey. These were large, coordinated observing programs designed to map the distant universe in multiple wavelengths and collect spectra, essentially the chemical and physical fingerprints of distant objects, from hundreds and eventually thousands of distant galaxies. And in this data, a curious pattern kept showing up. There were objects, sometimes dozens in a single field of view, that appeared very compact, much smaller than typical galaxies at similar distances. They were extraordinarily red, not just because of the redshift of their light, but with an additional redness that suggested they were embedded in or obscured by significant amounts of dust. Their brightness was high, surprisingly, sometimes shockingly high, for their apparent size. And when astronomers got spectroscopic data on them, confirming their distances and allowing a closer look at what kind of light they were emitting, things got even stranger. One of the first major papers to draw widespread attention to this phenomenon came from a team led by researchers, including Ivo Labbé at Swinburne University of Technology in Australia. They identified a sample of these massive red compact objects and made a startling claim. If the objects were as distant as they appeared to be, at redshifts of around 7 to 10, corresponding to the universe being only about 500 to 800 million years old, then they were extraordinarily, perhaps impossibly, massive. The total stellar mass, the combined mass of all the stars in these objects, seemed to be in some cases on the order of tens of billions to even hundreds of billions of solar masses. That's comparable to the mass of a large mature galaxy like the Milky Way. But these objects supposedly existed when the universe was less than 1 billion years old. Here's why that's a problem. The Milky Way has been building up its stellar mass for roughly 13 billion years. Stars form from gas clouds, and gas needs to cool and collapse, and that process takes time. You can't just snap your fingers and create a galaxy's worth of stars in a few 100 million years, or at least you shouldn't be able to, based on everything we understood about galaxy formation. The analogy that got thrown around a lot at the time was this. Imagine you're an archaeologist, and you're excavating what you think is a medieval site, roughly 800 years old, and you find a building that looks like it's made of modern reinforced concrete, with steel rebar and electrical wiring running through the walls. It doesn't fit. The technology to build something like that didn't exist 800 years ago. That's the kind of jarring mismatch we're talking about. These objects shouldn't be as massive as they appear to be, not if our models of galaxy formation are correct, not if our standard cosmological model is right. And yet, there they were. Now at this point, the natural scientific response is skepticism. Could there be measurement errors? Could the redshifts be wrong? Could the mass estimates be off? These were all valid questions, and scientists asked them vigorously. And in some cases, some of the earliest, most extreme claims did get revised as better data came in. A few objects that initially seemed impossibly massive turned out to be somewhat less extreme once spectra confirmed their exact distances. But here's the thing, even after all the careful scrutiny, even after throwing out the most extreme outliers, there remained a core population of objects that were genuinely, stubbornly anomalous. They were real, they were distant, and they didn't fit. And then, as more spectroscopic data came in, a new twist emerged that made things considerably more complicated and considerably more interesting. Chapter 4: Broad Lines, Black Holes, and the AGN Hypothesis. Spectroscopy is one of the most powerful tools in astronomy. When you spread out the light from a distant object into its component wavelengths, like a prism spreading white light into a rainbow, you can read an enormous amount of information encoded in that spectrum. The specific wavelengths at which light is absorbed or emitted tell you about the chemical composition of the object. The overall shape of the spectrum tells you about its temperature, and the width of specific emission lines, the sharp spikes of light at particular wavelengths caused by specific atomic transitions, tells you about the velocities of the gas that's emitting the light. When astronomers started getting detailed spectra of the little red dots, something jumped out immediately. The emission lines were broad, very broad. In astronomical spectroscopy, broad emission lines are a telltale signature. They occur when gas is moving at extremely high velocities, thousands of kilometers per second, which causes the Doppler effect to broaden the emission line across a range of wavelengths. And gas moving that fast in a compact region means one thing: it's orbiting something extremely massive. Specifically, it's the signature of gas swirling around a supermassive black hole in what's called an active galactic nucleus, or AGN. An AGN is essentially a feeding black hole. When a supermassive black hole is actively accreting material, pulling in gas and dust from its surroundings, that material forms a superheated accretion disk that glows brilliantly across a huge range of wavelengths. The most extreme AGN are called quasars, and they're among the brightest objects in the universe, sometimes outshining entire galaxies by factors of thousands. And quasars have broad emission lines. That's one of the ways you identify them. So when broad lines showed up in the spectra of the little red dots, a new hypothesis emerged. Maybe these aren't just compact, overly massive galaxies. Maybe they're AGN, maybe at their hearts they are actively feeding supermassive black holes, and it's the light from the accretion process, not just from stars, that's making them so bright and so compact looking. This was actually somewhat reassuring at first. AGN have been observed in the early universe before. We know supermassive black holes existed early on. There are quasars known at very high redshifts, meaning they existed when the universe was very young, so the existence of AGN at the distances implied by the little red dots wasn't inherently shocking. But then people started asking about the masses of these black holes, and things got complicated again. When you have a spectrum with broad emission lines, you can use the width of those lines, combined with the brightness of the object, to estimate the mass of the central black hole. This is called the virial method, and while it has uncertainties, it's a well-established technique. The black hole masses that came out of these calculations were startling. We're talking about objects where the central black hole might have a mass of tens of millions, or in some cases hundreds of millions, or even billions of solar masses, at redshifts of 4, 5, 6, 7, corresponding to times when the universe was only 1 to 2 billion years old. And this is where the problem gets really acute, because we actually don't know how supermassive black holes form and grow. This is already one of the outstanding problems in astrophysics. The leading theory is that they started as smaller seed black holes, perhaps the remnants of the first massive population 3 stars, or perhaps formed through the direct collapse of massive gas clouds, and then grew over billions of years by accreting matter and merging with other black holes. But even with our most optimistic models of how fast a black hole can grow, getting from a small seed to a billion solar mass monster in just a billion years is extraordinarily difficult. You basically need the black hole to be accreting at or near its theoretical maximum rate, called the Eddington limit, continuously for that entire period. Some models allow for brief periods of super Eddington accretion, growth faster than the theoretical maximum, but those are exotic and not well understood. And yet here are these little red dots, apparently hosting massive black holes when the universe is still in its cosmic infancy. But wait, there's another twist. Because when you look at the actual brightness of the little red dots, and more importantly, at the ratio of black hole mass to the mass of the surrounding galaxy, something deeply unusual shows up. Cert Chapter 5, The Overweight Black Holes. Problem. In the nearby universe, there's a remarkably tight relationship between the mass of a supermassive black hole and the mass of the stellar bulge, the central spherical component of its host galaxy. This relationship, sometimes called the M-sigma relation, or simply the black hole bulge correlation, tells us that the black hole is always roughly 1/10 of 1%, 0.1%, of the mass of the stellar bulge. This relationship is found across an enormous range of galaxy types and masses, which tells us something deep. The growth of black holes and the growth of galaxies are fundamentally linked. They co-evolve. The processes that feed one feed the other. This relationship is a cornerstone of our understanding of galaxy evolution. In the little red dots, this relationship appears to be wildly violated. In some cases, the estimated black hole mass is not 0.1% of the stellar mass, but something more like 10%, 30%, or in extreme cases even comparable to the total stellar mass. The black holes are, relative to their host galaxies, enormous, way more massive than they should be given the amount of starlight, and therefore the number of stars we can measure. This overweight black hole phenomenon is deeply puzzling. It could mean several different things. One possibility is that in the early universe, black holes really did grow faster than galaxies. The feedback mechanisms that normally regulate black hole growth weren't as effective in the early universe, allowing black holes to get ahead of their stellar bulges. This would be an important discovery about the physics of early galaxy formation. Another possibility is that there's a lot of star formation going on in these objects that we're not measuring correctly, that the galaxies are actually more massive in stars than our estimates suggest, perhaps because young, dusty regions of star formation are hiding a lot of stellar mass. If that's the case, the galaxy mass is being underestimated, which would bring the ratio closer to what we expect. A third possibility is that the black hole mass estimates are wrong, that the broad emission lines we're using to calculate black hole masses don't work the same way in these early extreme environments, and the virial method is giving us inflated answers. And there's a fourth possibility, one that's genuinely exotic, which we'll get to in a bit. But here's what makes things even more interesting, and what's really gotten theorists excited. Some of the little red dots don't just have overweight black holes, they have a spectral appearance that is deeply, profoundly weird in a very specific way. When you look at a typical AGN, a feeding black hole in the centre of a galaxy, the light you see has a characteristic spectrum. The accretion disk itself produces a bright, relatively blue-white continuum of light. The gas clouds surrounding the accretion disk, heated by its radiation, produce the broad emission lines we already talked about. And if there's dust around the AGN, it absorbs some of the shorter wavelength light and re-emits it at longer infrared wavelengths, making the object appear red. The little red dots tick most of these boxes, compact, red, broad lines, but some of them have a feature that's truly puzzling. They appear almost equally bright in both the blue visible wavelengths and the red infrared wavelengths, in a way that produces what spectroscopists describe as a V-shaped spectrum, or more technically, a spectrum with what looks like a combination of a blue, compact AGN-like component and a very red, dusty component, both simultaneously visible. This is strange because in a typical dust-obscured AGN, the dust completely blocks the shorter wavelength light. You wouldn't expect to see the blue component and the red component at the same time. It's like being able to see both the headlights of a car and the car perfectly clearly through a thick fog simultaneously. The fog that's making the car look red shouldn't also be letting the headlights through. One proposal is that these objects are viewed at a very specific orientation. Maybe we're looking slightly down the axis of the AGN's jet or accretion disk, through a patchy dust distribution that obscures some regions but lets light from others through. Another proposal is that the blue component isn't actually from the AGN itself, but from a vigorous burst of star formation happening simultaneously in the surrounding galaxy. Or perhaps some combination of both. Some researchers have even proposed that what we're seeing is gravitational lensing, the background object being magnified by the gravity of something in the foreground, which could make a fainter, more normal object appear unusually bright and compact. Lensing doesn't change the colours though, so it can explain some of the brightness anomaly, but not all of the spectral weirdness. The honest answer, as of the time of this video, is that none of these explanations fully account for everything we're seeing in the little red dots. There are multiple observations that each individual hypothesis can explain, but no single coherent model that explains everything at once. And that's actually one of the most exciting things about this whole situation, because when that happens in science, when you have a genuinely anomalous observation that none of your existing frameworks can fully account for, you know you're potentially standing at the edge of something genuinely new. Chapter 6: Galaxy Formation. Why this is so hard to explain. Let's zoom out for a moment and talk about why galaxy formation theorists are finding all of this so difficult to incorporate into their models. Because it's not for lack of trying. People have been running simulations, tweaking parameters, proposing new physics, and they're running into walls. Modern galaxy formation simulations, the most sophisticated ones, like illustrious TNG, Eagle, and more recently the Flares and Thiessen simulations, are extraordinarily complex pieces of software. They model the gravitational collapse of dark matter, the cooling and collapse of gas into galaxies, the formation of stars, the energetic feedback from those stars and from black holes that drives gas out of galaxies, the merging of galaxies over cosmic time. They've been tuned and tested against observations of the nearby universe, and they do a remarkable job of reproducing the galaxy population we observe locally. But when you run these simulations to the epoch that Webb is observing, the first billion years, and compare them to what Webb is actually seeing, the mismatch is stark. The simulations predict fewer massive galaxies in the early universe than Webb is finding. They predict smaller black holes at these redshifts. They predict that the extreme compactness of the little red dots shouldn't be as common as it appears to be, and they certainly didn't predict objects with the weird spectral properties we've been discussing. Now, a few caveats. Simulations are always approximations. The underlying physics of processes like star formation and AGN feedback, what's called subgrid physics because it happens on scales too small for the simulations to resolve directly, has to be parameterized and approximated. Different simulations make different choices, and they can produce somewhat different results. There's also a question of cosmic variance. The little patches of sky that Webb is looking at might not be perfectly representative of the universe as a whole. Maybe we've happened to point at unusually overdense regions where structure formed earlier and faster, but the size of the discrepancy between what the simulations predict and what Webb is finding is large enough that many researchers think it can't just be simulation artifacts or cosmic variance. The standard model of cosmology and galaxy formation, as powerful and well-tested as it is, may be missing something important about the early universe. What could that something be? Several ideas are on the table. Some researchers think the efficiency of star formation in the early universe was higher than our models assume, that a greater fraction of available gas was converted into stars more rapidly than we currently think is possible. Others think the feedback mechanisms that normally suppress star formation, supernovae blowing gas out of galaxies, AGN heating the surrounding gas, were less effective in the early universe, allowing galaxies to grow faster. Others think we need to rethink our assumptions about dark matter or about the initial conditions of the universe after the Big Bang. And then there are the more radical proposals, ideas that, if correct, would require fundamental changes to cosmology rather than just tweaks to galaxy formation physics. But before we get to those, let me tell you about some specific objects that have really crystallized all of this. Because sometimes in science, the abstract becomes very concrete when you focus on a specific remarkable example. Chapter 7. Meet the objects that are breaking models. Let's talk about some of the specific little red dot candidates that have received the most scientific attention because they illustrate the problem vividly. One of the most discussed early examples came from the CEERS survey, Cosmic Evolution Early Release Science. In images from CEERS, researchers identified a set of objects at very high redshift that appeared extremely compact, extremely red, and surprisingly bright. When spectra were obtained, several of them showed clear broad line signatures, confirming the presence of AGN activity, and their estimated black hole masses came out in the range of tens of millions to hundreds of millions of solar masses, at a time when the universe was less than 1 billion years old. A specific object that attracted enormous attention was one dubbed Maisie's Galaxy, named after the daughter of one of the researchers because its discovery happened on her birthday. While Maisie's Galaxy itself is primarily a galaxy rather than an AGN, its extreme redshift, later spectroscopically confirmed, placed it at a distance corresponding to the universe being only about 390 million years old, and it was more luminous and apparently more massive than it should be at that age according to standard models. It became something of a symbol for the broader tension between what Webb was finding and what models predicted. But perhaps the most striking examples have come from a class of little red dots that are simultaneously showing AGN signatures and what appear to be signatures of massive stellar populations. These dual-component objects, showing both an AGN and a massive galaxy at the same cosmic time and in the same compact space, are particularly challenging. They suggest that in the early universe, black holes and galaxies may have grown in a way that's fundamentally different from what we see in the later universe. And then there's what the scientists have started calling Little Red Dot 1 and related objects in the JADE survey, among the most thoroughly characterized members of this class. The JADE survey combined ultra-deep imaging from Webb's NIRCam instrument with follow-up spectroscopy from NRSpec, collecting detailed spectra of thousands of objects in 2 small patches of sky. Among those, the little red dot population stood out clearly, compact, red, with broad emission lines large inferred black hole masses, and this peculiar V-shaped spectral feature. The JWST team found that these objects were not rare one-off curiosities. They appeared throughout their survey fields with a frequency that implied they were a genuine population, a phase perhaps that many or most early massive black holes go through. The number density of these objects, how many of them exist per unit volume of the early universe, was surprising. In some mass and luminosity ranges, there are more of them than our models predicted there should be AGN of any kind at those distances. This abundance is itself important data. It tells us something about how common these objects are, which constrains theories about how they form and evolve, and the number is high enough that theorists have had a hard time explaining it within standard models, but as striking as all of this is the masses, the black hole properties, the spectral weirdness, the abundance. There's one more layer of strangeness that I've been saving, because I think it's in some ways the most thought-provoking aspect of this whole story. Chapter 8. The compactness problem and what it implies. Let's talk about size, specifically how small these things are. The little red dots are extraordinarily compact. When we measure their angular size on the sky, how many arcseconds they span, and convert that to a physical size at their inferred distances, we get objects that are often just a few hundred parsecs across. 1 parsec is about 3.26 light-years. A few hundred parsecs is hundreds of light-years. For context, the Milky Way is roughly 50,000 parsecs across. These little red dots are, in some cases, several hundred times smaller than the Milky Way in extent, but containing comparable or larger masses. This extreme compactness, this enormous mass crammed into a tiny volume, has implications for the density of these objects that are staggering. The stars and gas in these objects would be packed together at densities far exceeding anything in normal galaxies. The environments inside them would be extreme in ways that are difficult to model. This compactness is actually related to something interesting in the debate about what these objects are. If you have an object that's very compact and very bright, and you're trying to figure out what's powering it, the compactness gives you a clue. Stars alone, distributed over a tiny volume, would interact with each other in complex ways. Collisions, mergers, disruption events. The radiation pressure from such a dense burst of star formation would tend to blow the gas away very quickly, shutting off the star formation. It's difficult to maintain such an extreme starburst in such a small region without some other mechanism stabilizing it. On the other hand, an AGN, a feeding black hole, is, almost by definition, compact. The light comes from a region not much larger than the solar system, with the surrounding gas clouds extending perhaps a few hundred light-years. An AGN can naturally produce the kind of compactness we're seeing, but here's the subtlety. Some of the little red dots show evidence for stellar populations that are not negligible. The light from stars, alongside the AGN light, contributes measurably to the spectrum. So we have, compressed into a tiny region, both a massive stellar population and an extremely active black hole. And this brings up an idea that's been circulating in the theoretical community. The possibility that in the very early universe, before feedback mechanisms had time to act, there were periods of extraordinarily concentrated, intense simultaneous black hole growth and star formation happening in regions that were physically tiny. A kind of cosmic pressure cooker, and the little red dots might be what those pressure cookers look like to a telescope a billion years later. If that's what they are, concentrated, simultaneous black hole and galaxy growth events, then they might represent the seeds from which today's massive galaxies grew. The big elliptical galaxies we see in the centres of galaxy clusters, the most massive galaxies in the universe, they might have once gone through a little red dot phase. This would be a profound insight into galaxy evolution, essentially revealing the dramatic, compressed early chapters of the life story of the universe's most impressive structures. But of course, the story doesn't end there, because there are some researchers who think the little red dots are pointing to something even more fundamental, something that might require us to revisit the very framework of cosmology itself, and that's where things get genuinely wild. We'll get into that in the next part of this video, but before we do, I want to make sure you're appreciating the full weight of what we've covered so far, because I think it's easy to hear a list of anomalies and kind of nod along without fully feeling the impact. Imagine spending decades building the most sophisticated models of how the universe evolves, models that successfully explain the distribution of galaxies, the cosmic microwave background, The abundance of chemical elements, the large-scale structure of the universe, models that have passed test after test after test, and then you point a new telescope at the early universe. And in the very first few months of data, you start finding objects that don't fit. Not slightly don't fit, dramatically don't fit, in ways that are hard to sweep under the rug with small adjustments to parameters. That's where astronomers are right now. And the question of what to do with that, how to revise the models, what new physics might be needed, what these red dots are telling us about the very foundations of cosmology, is one of the most exciting and consequential open questions in all of science. Chapter 9. The Black Hole Seed Problem. Where did these monsters come from? So we've established that the little red dots appear to host supermassive black holes that are too massive, in galaxies that are too massive, existing at a time when the universe was too young for any of this to have happened according to our standard models. Now, let's dig into one of the deepest subproblems within this broader mystery, because it's one that was already keeping astrophysicists up at night long before Webb launched, and Webb has made it dramatically worse. The problem is this: we don't know where supermassive black holes come from. I want to let that sit for a second, because it's a remarkable admission for a field that has made such extraordinary progress over the past century. We know black holes exist. We've detected their gravitational waves. We've imaged them directly with the Event Horizon Telescope. We know supermassive black holes sit at the centres of essentially every large galaxy. We know they influence the growth and evolution of their host galaxies in profound ways. And yet the question of how they got there, how the first supermassive black holes formed and grew to their enormous sizes, remains one of the most poorly understood problems in all of astrophysics. The difficulty is fundamentally one of time. Growing a black hole to supermassive scales, billions of solar masses, takes an enormous amount of time if you're doing it the conventional way. You need a seed black hole to start with, then you need to feed it. And the maximum rate at which a black hole can accrete matter is governed by the Eddington limit, the point at which the radiation pressure from the infalling material becomes so intense that it pushes the surrounding gas away, shutting off the accretion. At the Eddington limit, a black hole can double its mass roughly every 45 million years or so. That sounds fast, but consider, if you start with a stellar mass black hole of, say, 10 solar masses, and you let it accrete continuously at the Eddington limit, it takes several billion years to reach 1 billion solar masses. That's most of the current age of the universe, and it assumes zero interruptions, zero periods of slower accretion, zero time spent without a ready supply of gas to consume. But the little red dots are showing us billion solar mass black holes at redshifts, where the universe is only 1 billion years old. Mathematically, this doesn't work if you start from a small seed and accrete at the Eddington limit. You simply cannot get there in time. So theorists have been proposing alternative pathways. 3 main categories of seed black hole formation have been on the table for years, and Webb's observations are now providing new pressure on each of them. The first category is stellar remnant seeds. When the very first massive population 3 stars died, exploding as supernovae or directly collapsing without an explosion, they left behind black holes. These would have had masses of perhaps a few tens to a few hundred solar masses. These are called light seeds. The problem with light seeds is exactly what I described above. Even with the most optimistic accretion history, it's very hard to grow a light seed into 1 billion solar mass black hole within 1 billion years. The second category is direct collapse black holes, or DCB centers. In this scenario, under very specific conditions in the early universe, specifically in regions where star formation is suppressed by intense radiation from nearby galaxies, preventing the gas from fragmenting into individual stars. Enormous gas clouds can collapse directly into black holes without first forming stars. These heavy seeds could start with masses of 100,000 to 1 million solar masses, which gives them a much better head start in the growth race. DCBHs are theoretically attractive, but they require very particular environmental conditions that may not be common, and we haven't detected one yet. Webb might be capable of seeing one. Some researchers think certain unusual high redshift objects could be DCBH candidates, but it's not confirmed. The third category involves runaway processes in dense stellar clusters, situations where young, massive stars in an extraordinarily dense cluster undergo rapid collisions and mergers, building up a very massive star that then collapses into a black hole of perhaps thousands of solar masses. Again, a more favourable starting point than a single stellar mass seed, but still not obviously sufficient to explain the most massive early black holes. Now, here's how the little red dots are making this problem worse. If we take their broad emission lines at face value and calculate their black hole masses using standard methods, and if we take their redshifts at face value, then we're not just looking at objects with massive black holes in the early universe, we're looking at a population of such objects, multiple examples spread across different fields of view, suggesting this isn't a 1 in a billion fluke, but rather a common outcome. A common outcome that our models say shouldn't be happening. One response has been to question whether the mass estimates are reliable. The virial method for estimating black hole masses from broad emission lines was calibrated using nearby AGN, where we have independent ways of checking the masses. It assumes that the broad-line region gas is in a specific kind of dynamical equilibrium, essentially that the gas is gravitationally bound to the black hole, and its velocity reflects the black hole's gravitational pull. But what if, in these extreme early universe environments, that assumption breaks down? What if the broad lines are broadened not just by orbital velocity but by outflows, gas being blown out of the system by radiation pressure or jets? That would make the lines artificially broad, leading to an artificially high mass estimate. This is a real concern, and some researchers have argued that at least some of the little red dots might host black holes that are less massive than the broadline method suggests. Not because the black holes aren't real, but because the measurement technique is being fooled. But here's the counter-argument. Even if you systematically reduce all the black hole mass estimates by a factor of 10, you still have a lot of massive black holes in the early universe. You haven't made the problem go away, you've just made it slightly less severe. And there's another piece of evidence that's hard to argue with: the sheer luminosity of these objects. However you model the spectrum, you need to explain where all the energy is coming from, and in many cases, even with generous assumptions about star formation, you still need an extremely energetic compact source, which, in astrophysics, means an actively accreting massive black hole. You can debate the exact mass, but you can't argue that the black hole doesn't exist, so the black hole seed problem remains, and Webb has sharpened it considerably. The question of where these massive black holes came from, how they got so big so fast, is going to be one of the central questions driving high redshift observational astronomy for the next decade. Chapter 10. Could the standard model of cosmology be wrong? Now we get to the really radical territory, the place where some researchers, careful, qualified, mainstream researchers, not fringe voices, are starting to ask genuinely unsettling questions about the foundations of cosmology. The lambda cold dark matter model, lambda CDM, is the standard model of cosmology. It describes a universe whose energy budget is dominated by two mysterious components: lambda, the cosmological constant, which represents dark energy and is responsible for the accelerating expansion of the universe, and cold dark matter, the invisible, non-interacting matter that provides the gravitational scaffolding on which galaxies and large-scale structure form. Ordinary matter, everything made of atoms including every star, planet, gas cloud and human being, makes up only about 5% of the universe's total energy content in this model. Lambda CDM has been extraordinarily successful. It predicted the detailed structure of the cosmic microwave background fluctuations, which were then confirmed with extraordinary precision by satellites like WMAP and Planck. It explains the large-scale distribution of galaxies. It accounts for the observed abundances of light elements produced in the first few minutes after the Big Bang. It is, by any reasonable measure, one of the most well-tested scientific frameworks ever developed. And yet, there are cracks. Not new cracks. Some of them have been known for years. But Webb has widened some of those cracks in ways that are hard to ignore. The most significant tension that Webb's little red dots create with lambda CDM involves what's called the halo mass function, essentially the predicted number of dark matter halos of different masses that should exist at different points in the universe's history. In lambda CDM, structure forms hierarchically. Small things form first, then merge into bigger things. The most massive structures form last. This means that in the early universe, there should be relatively few very massive dark matter halos, and by extension, relatively few very massive galaxies. The numbers should follow a specific distribution that the theory predicts with high precision. If the galaxies associated with the little red dots are as massive as they appear, their number density, how many there are per unit volume of the universe, may exceed what lambda CDM predicts for massive halos at those redshifts. You simply shouldn't have that many massive structures that early. The dark matter hasn't had time to cluster into halos massive enough to host them. Now, before we throw lambda CDM in the trash, let's be precise about the uncertainty here. The stellar mass estimates for early galaxies are difficult and have significant error bars. The spectroscopic confirmation of redshifts is not always available. Photometric redshift estimates, based on the colours of objects rather than detailed spectra, can be wrong. And as I mentioned, cosmic variance could mean that the specific fields Webb has observed are atypically overdense. Researchers have done careful statistical analyses trying to account for all of these uncertainties, and the conclusion is nuanced. The most extreme examples, the objects that would be most incompatible with lambda CDM if their properties are correct, may indeed be partially explained by measurement uncertainties and cosmic variance. But the overall excess of massive early galaxies compared to lambda CDM predictions is robust at a statistically significant level. It persists even in the conservative analyses. So what are the alternatives? What could be wrong with lambda CDM, and what might replace or modify it? One class of proposals involves modifying the nature of dark matter. Standard cold, dark matter consists of particles that move slowly and interact only gravitationally. This produces a specific pattern of structure formation that lambda CDM captures well at large scales, but has some issues at small scales. Warm, dark matter, made of particles that move faster, would suppress the formation of small structures, but might also change the formation of larger ones in ways that could, potentially, allow more massive structures to form earlier. Fuzzy dark matter, made of ultralight particles with quantum mechanical wave-like behaviour, has similar small-scale effects. Neither of these alternatives was specifically designed to explain the Webb results, but theorists have been exploring whether they might help. Another class of proposals involves modifications to inflation, the period of extremely rapid expansion in the very early universe, a tiny fraction of a second after the Big Bang. The quantum fluctuations generated during inflation are the seeds of all cosmic structure. The standard inflationary picture produces a nearly scale-invariant spectrum of fluctuations, roughly the same amplitude at all scales, but small modifications to inflationary models can produce enhanced fluctuations on certain scales, which could seed more massive structures earlier. If there was enhanced small-scale power in the primordial fluctuations, you'd expect more massive early galaxies, which is exactly what Webb might be seeing. A third class of proposals is more radical, modifications to general relativity itself, or to the dynamics of dark energy. Some researchers have proposed that the cosmological constant is not actually constant, that dark energy evolves over cosmic time. If dark energy was more influential in the early universe than lambda CDM assumes it could, potentially change the rate of structure formation in ways that might help explain the Webb results. But making this work quantitatively without breaking the excellent agreement with CMB observations and other data is very difficult. And then there's the most radical proposal of all, one that's been championed by a small but vocal group of researchers, most prominently perhaps the astronomer Rajendra Gupta, that the Webb results, combined with other tensions in cosmology, point to the possibility that the universe is actually much older than 13.8 billion years. Gupta and colleagues have argued that a combination of an evolving coupling constant, the constants of physics themselves changing over time, and a tired light component where photons lose energy over distance independently of cosmological redshift, could allow the universe to be several times older than current estimates. In such a universe, there would be ample time for galaxies and black holes to grow to the sizes we observe. This is a very fringe proposal. The tired light hypothesis was largely ruled out decades ago by observations that are inconsistent with it, including the time dilation of distant supernova light curves, which is exactly what you'd expect in an expanding universe, but not in a tired light scenario. Most mainstream cosmologists do not take this proposal seriously, but it illustrates the range of ideas being floated as people grapple with the Webb results. The most likely scenario, to be clear, is not that lambda CDM is fundamentally wrong, but that it needs adjustment, that our models of galaxy formation and black hole growth within the lambda CDM framework are missing some physics, something that makes the first stars and galaxies and black holes form and grow more rapidly than our current models allow. That's a much smaller and more tractable revision than overhauling the entire cosmological model. But even a relatively modest revision to galaxy formation physics could have profound implications for our understanding of the early universe, and that's worth taking seriously. Chapter 11. The Role of Dust. Are we being fooled? There's another angle to the little red dots mystery that I haven't fully addressed yet, and it's important because it gets at a very fundamental question. How much of what we're seeing is a genuine physical property of these objects, and how much is an observational artifact caused by something obscuring or modifying the light on its way to us? The answer, in short, is that dust is playing a major role in the appearance of the little red dots, and figuring out exactly how major is genuinely difficult. Dust in astronomy is not the same as the dust bunnies under your couch. Cosmic dust consists of tiny solid particles, silicon compounds, carbon compounds, various minerals, that are produced in the outflows of evolved stars and in the interstellar medium. These particles are excellent absorbers of ultraviolet and visible light, but they're relatively transparent to infrared light. So when light passes through a dusty region, the shorter wavelength blue light gets absorbed or scattered much more than the longer wavelength red and infrared light. The object appears reddened, not because it's intrinsically red, but because the blue light has been selectively removed. This is important because it means that some of the redness of the little red dots might not be telling us anything about their intrinsic nature. It might just be telling us that there's a lot of dust between us and the stars and black holes we're looking at. In that case, the apparent redness is an observational artifact, and the underlying object might be less extreme than it appears. But here's the complication. Dust is itself informative. The fact that these objects contain a lot of dust tells us something. Dust is made of heavy elements heavier than hydrogen and helium, which astronomers collectively call metals, and those elements were forged in stars. You can't have a lot of dust in the early universe without having had previous generations of stars that lived and died and scattered their heavy element-enriched material into the surrounding interstellar medium. In other words, a dusty object in the early universe implies a significant history of prior star formation. So the presence of dust in the little red dots is itself evidence of early, rapid, extensive star formation, which is exactly the kind of thing that challenges our models. Moreover, the amount of dust some of these objects appear to contain is extraordinary. Modelling the infrared emission and the spectral energy distribution, the distribution of energy across different wavelengths, of these objects suggests dust masses that are, in some cases, comparable to or exceeding anything we see in local galaxies of similar stellar mass. Having that much dust in a galaxy that's only a few 100 million years old requires an extremely rapid cycle of stellar birth and death. Yet another thing that strains our models. There's also a fascinating observational puzzle related to dust. Dust absorbs light and re-emits it at far infrared wavelengths that for very high redshift objects get shifted into the millimeter radio regime by the time they reach us. Several little red dots and similar high redshift objects have been observed with radio telescopes, specifically ALMA, the Atacama Large Millimeter/Submillimeter Array, looking for this far infrared dust emission. And in some cases, the results are puzzling. Some objects show less dust emission than you'd expect given their redness, which could mean the redness is not primarily due to thermal dust emission, but rather to some other reddening mechanism, or to a specific geometry of the dust distribution. Getting the dust geometry right is crucial. A smooth shell of dust uniformly covering an object will produce different spectral signatures than a patchy, clumpy dust distribution. In some models of the little red dots, the dust is arranged in a specific geometry, perhaps a thick torus or disk around the central black hole, similar to the obscuring torus seen in unified models of AGN, which could explain why we see some combination of direct AGN light and dust-reddened light simultaneously. The interplay between dust, star formation, and AGN activity in these compact early objects is extraordinarily complex, and disentangling them from photometry and spectroscopy alone is very challenging. What researchers really want is something more. High-resolution imaging that can spatially resolve the different components of these objects, mapping where the stars are, where the dust is concentrated, and where the AGN light is coming from. Webb's imaging resolution is remarkable, but even it struggles to spatially resolve objects that are only a few hundred parsecs across at redshifts of 5 or 6. The angular size we're dealing with is tiny, fractions of an arcsecond. But in some cases, particularly for objects that are slightly lower redshift or slightly larger, Webb's NIRCam instrument is beginning to show tantalizing hints of structure, a compact central source surrounded by a fainter, extended envelope of emission, or asymmetric features that might indicate recent mergers or outflows. And this brings up another tool that astronomers are beginning to use to study these objects: gravitational lensing. When a massive foreground object, a galaxy cluster for instance, sits between us and a distant background object, its gravity bends and magnifies the light from the background object, acting like a natural cosmic telescope. Some of the best studied little red dot candidates have been identified behind known galaxy clusters, where the lensing magnification allows us to see them in much greater detail than would otherwise be possible. Using lensing, researchers have been able to probe the internal structure of some of these objects at levels of detail that would otherwise be inaccessible. The picture that's emerging from these detailed studies is of objects that are genuinely extreme in multiple ways simultaneously. Extremely compact, extremely dusty, extremely energetic, hosting both vigorous star formation and active black hole accretion. Not just one extreme property that might be explained away, but a constellation of extreme properties that all have to be accounted for together. Chapter 12. Spectroscopic Confirmation. The ground truth. Throughout this video I've been using phrases like apparently, seems to be, and appears to have when discussing the properties of the little red dots. That's deliberate, because in observational astronomy there's always a crucial distinction between what the data suggests and what has been rigorously confirmed. The most important form of confirmation in extragalactic astronomy is spectroscopy. Photometric observations, measurements of an object's brightness through different filters, can tell you a lot, but they can also mislead. An object that appears very red and very distant based on its photometric colours might turn out, upon spectroscopic examination, to be a nearby dusty galaxy at much lower redshift. These photometric redshift catastrophes are a known hazard in high redshift galaxy surveys, so spectroscopic confirmation is essential, and this is where Webb's NIRSpec instrument, its near-infrared spectrograph, has been absolutely transformative. NIRSpec can observe spectra of up to 100 objects simultaneously using a system of tiny shutters called a microshutter array, which can be configured to pass light from specific objects while blocking everything else. This multiplexing capability has made it possible to collect confirmed spectra with precise redshift measurements for hundreds of little red dot candidates, far more than would have been possible with earlier instruments. The results of these spectroscopic campaigns have been important in several ways. First, they've confirmed that many of the photometrically selected little red dot candidates really are at the high redshifts implied by their colours. The photometric redshift estimates, while not perfect, have been broadly correct for this population. This is reassuring. It means the basic picture of these being genuinely high redshift objects is not an artifact of photometric errors. Second, the spectra have revealed the broad emission lines that indicate AGN activity in a substantial fraction of the population. In some surveys, roughly half or more of the compact red objects at high redshift show broadline AGN signatures. This fraction is astonishingly high compared to what we'd expect based on our understanding of the AGN population at lower redshifts. Third, the spectra have revealed some unexpected emission line ratios, the relative strengths of different atomic emission lines, that are unusual compared to both normal galaxies and normal AGN at lower redshifts. Some of these unusual ratios might be explained by the extreme physical conditions in the little red dots. Very high gas densities, very high ionization states, potentially unusual chemical abundances, but some of them are genuinely puzzling and not easily explained by any standard model. One particularly interesting spectroscopic feature found in some little red dots is an unusually strong hydrogen Balmer break, a feature in the spectrum at a specific ultraviolet wavelength that's caused by absorption of light by hydrogen atoms in a certain energy state. A strong Balmer break is characteristic of relatively old stellar populations, stars that are at least a few hundred million years old. Finding this signature in galaxies at very high redshift, where the universe is only a few hundred million years old, implies that the stars in these objects formed very early, essentially as soon as it was physically possible to form stars, and then had some kind of star formation quenching event that reduced or stopped the formation of new stars while the old ones aged. This is yet another piece of the puzzle that challenges standard models, which don't easily produce massive, old stellar populations in the very early universe. There's also an intriguing tension between two common interpretations of the little red dot spectra. If you assume the broad lines are caused by AGN activity, you get one set of inferences about the object's properties: a massive black hole, a potentially lower stellar mass. If you assume the broad lines are caused by outflows or very turbulent star-forming gas rather than AGN activity, you get a different set of inferences, potentially an extreme starburst, without necessarily requiring a massive black hole. Some researchers have argued passionately for the starburst interpretation, noting that the extremely high star formation rates implied by the luminosities of some little red dots could produce broad lines through stellar winds and supernova-driven outflows. Others argue equally passionately that the line widths are simply too broad to be explained by anything other than a black hole's gravity. The truth may well be that both processes are occurring simultaneously in at least some of these objects, that we're looking at systems where a feeding black hole and an intense starburst are both happening at once, feeding off the same reservoir of dense gas in a tiny, intense region of the early universe. In that case, both interpretations are partially right, and the debate is somewhat misframed. Getting to the truth will require even more spectroscopic data, deeper spectra that can detect fainter emission lines and absorption features, and ideally spatially resolved spectroscopy that can map the properties of these objects across their extent, rather than averaging over everything in a single spectrum. Chapter 13. What are they evolving into? Here's a question that shifts our perspective usefully. If the little red dots are real, if they're genuinely compact, massive objects hosting overgrown black holes in the early universe, what do they become? What do they look like today, 13 billion years later? This is a question of cosmic evolution, and it's one of the most exciting aspects of the little red dot phenomenon, because every object we observe in the early universe is in some sense an ancestor of something we can observe in the nearby universe. Understanding the connection between distant high redshift objects and nearby galaxies is one of the central goals of observational cosmology. The leading hypothesis is that the little red dots represent the progenitors, the ancestors, of what we call compact massive galaxies, or red and dead galaxies. In the local universe, there's a population of massive elliptical galaxies that are essentially done forming stars. They're called red and dead because their stellar populations are old and red, and they're no longer star-forming. These galaxies are found preferentially in the centers of galaxy clusters, and they contain some of the most massive black holes known. The Milky Way, our home galaxy, is not one of these. It's still actively forming stars and has a relatively modest central black hole. But the giant elliptical galaxies at the centers of large clusters, like the famous galaxy M87 that harbors a black hole we've directly imaged, are the kind of objects we're talking about. The connection to the little red dots would go something like this. In the first billion years of the universe's history, the progenitors of today's massive ellipticals underwent an extreme phase of simultaneous black hole growth and star formation in a very compact region. This is the little red dot phase. The intense AGN activity during this phase drove powerful outflows that expelled gas from the galaxy, shutting down the star formation, a process called quenching. After quenching, the galaxy continued to grow in size through mergers with smaller galaxies over the subsequent billions of years, a process called size growth, while its stellar mass remained roughly constant or grew more slowly. By today, the galaxy has grown from a compact little red dot to a large, puffy, red and dead elliptical. This scenario, called inside-out growth, is actually predicted by some models of galaxy evolution and is supported by observations of intermediate redshift galaxies that appear to be in transition states between the little red dot phase and the fully evolved elliptical phase. The fact that Webb is now showing us the little red dot phase in such clear detail provides a crucial anchor point for this evolutionary sequence. If this picture is correct, and it's gaining support, then the little red dots are not anomalous freaks. They're the normal, if brief and extreme, early chapter of the life story of the universe's most massive galaxies, and the overweight black holes we see in them are the seeds of the most massive black holes that exist today, including the ones like M87s that we can now image directly. That's a remarkable thought. The black hole in M87, the one in that famous first image, may have once been the tiny, overweight, overfed engine at the heart of something that looked like a little red dot, 13 billion years ago as seen by whoever happened to be watching from across the universe. JWST, Chapter 14, New Data, New Confusion. The story is still evolving. One of the things I want to make sure is clear in this video is that this is not a resolved story. This is not a chapter that has been written and closed. This is an ongoing, active, sometimes contentious scientific debate, and the ground is shifting under our feet as new data keeps coming in. In 2024, multiple new analyses of little red dot samples have been published or posted to preprint servers, and they've collectively both clarified and complicated the picture. On the clarifying side, there's now much stronger spectroscopic confirmation that these objects are at the high redshifts implied by their colours. The broad emission lines are real, and they really do indicate the presence of rapidly moving gas, almost certainly associated with AGN activity in most cases. The high apparent stellar masses and black hole masses are not simply photometric artifacts. On the complicating side, some recent analyses have raised new questions about whether the standard methods for interpreting these spectra, methods developed for lower redshift objects, are fully applicable in these extreme environments. A paper that attracted considerable attention argued that in some little red dots, the broad hydrogen emission lines, the Baemer lines, show an unusual profile that's not easily explained by standard AGN models. Specifically, the lines appear to have a combination of narrow and broad components in proportions that are atypical. This could indicate that the gas dynamics in these systems are more complex than assumed, perhaps involving inflows as well as outflows or multiple kinematically distinct components of gas. Another recent development involves what might be called the number density crisis. As the spectroscopic samples have grown, researchers have refined their estimates of how many little red dots exist per unit volume of the universe. And the numbers, in some studies, are even higher than initial estimates suggested. In the redshift range from about 4 to 8, covering the period from roughly 600 million to 1.5 billion years after the Big Bang, the number density of broadline AGN implied by the little red dot sample is orders of magnitude higher than predictions based on extrapolating from lower redshift AGN surveys. This is a dramatic claim that has serious implications for our models of black hole growth and AGN evolution. However, and this is important, there are uncertainties in the selection effects here. Little red dots are selected in a specific way, based on their compactness and redness. This selection might be preferentially picking up objects with certain viewing geometries, or certain dust configurations, or certain ranges of black hole mass. Correcting for these selection effects to get a true population number density is very difficult, and different teams have come up with significantly different results depending on their assumptions. The debate is genuine and ongoing. Some researchers think the number density excess is very real and very large. Others think it can be largely explained by selection effects and measurement uncertainties. Most are somewhere in between. What everyone agrees on is that there's something here. These objects are real, they're numerous, they're challenging to explain, and they're going to require more data and more careful analysis to fully characterize. And more data is coming. Webb is continuing to observe. The NUSPEC micro-shutter assembly is continuing to collect spectra. New deep field surveys are being planned and executed. Complementary observations with ALMA are mapping the dust and molecular gas in these objects. And there's a new generation of extremely large ground-based telescopes on the horizon. The Extremely Large Telescope, the 30-meter telescope, the Giant Magellan Telescope, that will offer spectroscopic capabilities that surpass even Webb in certain wavelength ranges and spectral resolutions. The next few years are going to be extraordinary for high redshift astronomy. The pace of discovery and the quality of data are both increasing rapidly. Whatever the little red dots turn out to be, whatever combination of exotic physics and extreme astrophysics is needed to explain them, the answer is within reach. And the implications of that answer could be profound. Chapter 15. The Theorists Strike Back. New models for a new reality. When observations challenge theory, theorists have two choices. They can dig in and defend the existing framework, arguing that the observations are being misinterpreted, or that measurement errors explain the discrepancy. Or they can do what good scientists always eventually do. They can update the theory. Right now, across universities and research institutes around the world, theoretical astrophysicists are doing exactly that. They're building new models, running new simulations, and proposing new physical mechanisms that might explain what Webb is showing us. And the diversity of approaches is remarkable. It reflects both the richness of the problem and the genuine scientific uncertainty about which direction the solution lies. Let me walk you through some of the most interesting theoretical developments, because understanding where the theory is going helps illuminate what's at stake in this whole mystery. One of the most actively developed theoretical frameworks is what's being called super-Eddington accretion. Remember the Eddington limit, the theoretical maximum rate at which a black hole can accrete matter, set by the point at which radiation pressure balances gravity and pushes the infalling gas away. Standard models of black hole growth assume that black holes don't significantly exceed this limit, at least not for sustained periods. But there's been growing theoretical work suggesting that under certain conditions, particularly in the dense gas-rich environments of the early universe, black holes might be able to exceed the Eddington limit by significant factors. In super-Eddington accretion, gas falls in faster than the radiation can push it away, perhaps because the geometry of the accretion flow allows radiation to escape primarily along certain directions while matter continues to fall in along others. Simulations of super-Eddington accretion flows have shown that this is physically plausible, at least in principle, and can produce black hole growth rates several times the Eddington rate. If super-Eddington accretion was common in the early universe, which the dense gas-rich conditions of that epoch might favour, then the time needed to grow from a seed black hole to 1 billion solar masses could be dramatically reduced. You might be able to get there in a few 100 million years rather than several billion. This would go a long way toward explaining the massive black holes we see in the little red dots. But super-Eddington accretion also has specific observational signatures. It tends to produce powerful outflows and jets, driven by the intense radiation pressure, and the spectral signature of a super-Eddington accretor looks somewhat different from a standard AGN. It tends to produce more soft X-ray emission and has a different ultraviolet continuum shape. Some researchers have argued that the peculiar spectral properties of the little red dots, including that strange V-shaped continuum we discussed earlier, might actually be consistent with super-Eddington accretion viewed at certain orientations through certain dust configurations. It's an intriguing hypothesis that several groups are actively testing with new data. Another theoretical development involves what's been called early galaxy formation efficiency enhancement. This is a more incremental modification to existing models, not invoking new physics exactly, but changing the parameters of known physical processes. The basic idea is that the first generation of star-forming clouds in the early universe might have been more efficient at converting their gas into stars than typical molecular clouds today. Modern star-forming regions, like the Orion Nebula in our own galaxy, convert only a few % of their available gas into stars before feedback from newly formed stars disrupts the cloud and prevents further star formation. But what if, in the early universe, with different metallicities and different radiation environments and different gas dynamics, that efficiency was higher? If even 20 or 30% of the gas in early clouds converted to stars, you could build up stellar mass much faster than our models currently assume. Recent work has shown that small increases in star formation efficiency can have outsized effects on the predicted number of massive early galaxies. A factor of 2 or 3 improvement in efficiency might be enough to bring the model predictions into agreement with Webb's observations, without requiring any exotic new physics. The challenge is explaining why the early universe would be more efficient, what physical mechanism produces that difference, and then testing that mechanism against other observations. A related proposal involves the role of cosmic environment. In the standard picture of cold dark matter structure formation, the first massive dark matter halos form preferentially in the densest regions of the primordial density field, the peaks of the initial quantum fluctuations that were laid down during inflation. These regions are the seeds of what will eventually become galaxy clusters, and the galaxies that form in these overdense regions experience a different environment from galaxies that form in more typical or underdense regions. They have access to more gas, they experience more mergers, their star formation may be accelerated by the compression of gas in dense filaments and sheets. Some theorists have proposed that the little red dots might be preferentially located in these extreme overdense regions, that we're seeing the brightest, most extreme members of early protoclusters, the regions that will eventually collapse into the massive galaxy clusters we see in the nearby universe. In that case, the little red dots might not be representative of typical galaxies at high redshift, but rather the exceptional tip of the iceberg, the most extreme outcomes of structure formation in the densest cosmic environments. If true, this would mean our models don't need to be wrong for typical galaxies. They just need to allow for rare, extreme environments where things develop much faster. Cosmic variance, in other words, but at a more physically motivated level than simple random fluctuations. There's actually some observational support for this idea. Several little red dots have been found in close spatial proximity to each other or to other high redshift galaxies, suggesting they might be part of early protoclusters. The JD survey in particular has identified several structures at high redshift that look like they could be the early stages of what will eventually be large galaxy clusters, and several of those structures contain little red dot candidates. If the little red dots are indeed preferentially found in overdense environments, that's an important clue about their nature and formation. But, and this is crucial, even if the most extreme little red dots are in overdense regions, there are enough of them scattered across the sky that not all of them can be in protoclusters. Some of them appear to be in relatively isolated environments. So the protocluster explanation might account for some of the abundance excess, but not all of it. Chapter 16. Primordial black holes. The wildest hypothesis. Now, I want to tell you about an idea that's genuinely out there. Not mainstream, but seriously discussed by serious people, and worth understanding because of what it would mean if it were true. The idea is primordial black holes. Primordial black holes are black holes that didn't form from the collapse of stars. They formed directly from the extreme density fluctuations of the very early universe, fractions of a second after the Big Bang, when regions of space that were denser than their surroundings by a critical amount collapsed directly into black holes before any stars or galaxies existed. These are not hypothetical objects in the sense of being physically impossible. The mechanism by which they would form is well understood in principle. The question is whether the primordial density fluctuations were large enough and frequent enough to actually produce them in significant numbers. Primordial black holes have a long history in theoretical cosmology, and they've been proposed as candidates for dark matter. If they exist with masses in the right range, they'd be gravitationally interacting but electromagnetically invisible, fitting the observational definition of dark matter. Various astronomical surveys have constrained the abundance of primordial black holes at different mass ranges by looking for microlensing events, instances where a primordial black hole passes in front of a background star and briefly brightens it through gravitational lensing. These constraints are now quite tight across a wide range of masses, ruling out primordial black holes as the dominant component of dark matter in most mass ranges. But here's where the little red dots come in. Some researchers have proposed that even if primordial black holes don't make up all of dark matter, they might have formed in significant numbers with masses in the range of thousands to millions of solar masses, the heavy seed mass range. In that case, they could provide a natural and abundant source of seed black holes that were already massive when the first stars and galaxies formed. These primordial black hole seeds wouldn't need to grow from stellar mass seeds through billions of years of accretion. They'd start big, and they could then grow further through gas accretion in the gas-rich early universe, potentially reaching the billion solar mass scales implied by the little red dot observations much more easily than seeds formed from stellar remnants. The primordial black hole seed hypothesis is attractive precisely because it sidesteps the time problem. If your seed is already a million solar masses, growing it to a billion solar masses in a few 100 million years through Eddington-limited accretion becomes plausible. It only requires about 20 e-folding times rather than 40 or more starting from a stellar mass seed. But there are serious challenges with this hypothesis. First, producing primordial black holes with masses in the 1,000 to million solar mass range requires very specific conditions in the early universe. Specifically, a significant enhancement of primordial density fluctuations at certain scales. Standard inflation doesn't produce this naturally, so you'd need a non-standard inflationary model. Second, if primordial black holes were common enough to provide seeds for all the little red dots we're seeing, they'd likely also produce detectable signatures in the gravitational wave background, the stochastic sea of gravitational waves from countless black hole mergers throughout cosmic history. The gravitational wave background has now been detected by pulsar timing arrays, and characterizing its properties might eventually allow us to constrain or test the primordial black hole scenario. Third, and this is perhaps the most fundamental issue, Primordial black holes as heavy seeds would only explain the black hole masses. They don't by themselves explain the stellar masses of the host galaxies, the extreme dust content, the compact morphologies, or any of the spectral weirdness of the little red dots. They solve one part of the puzzle but leave many other parts untouched. So while the primordial black hole hypothesis is interesting and worth keeping on the table, it's probably not a complete solution to the little red dot mystery on its own. At best, it might be one component of a more complete picture. Chapter 17. What quasars in the early universe tell us before Webb. We already knew that massive black holes existed in the early universe because we had detected quasars at very high redshifts. The most distant quasars known, objects like J0313-1806 discovered in 2021, exist at redshifts above 7, meaning we see them as they were when the universe was less than 700 million years old. Their inferred black hole masses are staggering, in the range of hundreds of millions to a billion solar masses, and they were already a serious challenge for models of black hole formation and growth before Webb ever launched. So what do these known high redshift quasars have to do with the little red dots? Are they the same kind of object or different? The relationship is subtle and important. High redshift quasars like J0313-1806 are extraordinarily bright enough to have been detected by ground-based surveys operating in the optical and near-infrared. They're among the most luminous objects in the universe, powered by black holes that are accreting at or near the Eddington limit. Because of their extreme brightness, they can be detected even though they're enormously far away. The little red dots, by contrast, are typically much fainter. They're detectable by Webb because Webb is extraordinarily sensitive, but most of them would have been completely invisible to ground-based high redshift quasar surveys. They occupy a lower luminosity range. They might have smaller black holes, or be accreting at a lower fraction of the Eddington rate, or be more heavily dust obscured so that less of their light escapes in the observed wavelength range. This distinction is crucial. The known high redshift quasars are the tip of the iceberg, the absolute most extreme, most luminous examples of early massive black holes that happen to be bright enough and unobscured enough to be detected by earlier instruments. The little red dots, on the other hand, might represent the broader population of early massive black holes, the main body of the iceberg that was previously hidden below the detection threshold. If that's correct, then the implications are significant. The number density of massive black holes in the early universe might be much higher than the known quasar population suggested, and the typical properties of early massive black holes, their dust content, their relationship to their host galaxies, their spectral characteristics, might be better represented by the little red dots than by the rare, extreme high redshift quasars. Think of it this way. If you wanted to understand the human population of a city, you wouldn't just study the 100 richest people, you'd need to study the full distribution. The middle class, the working class, everyone. The known high redshift quasars are like those 100 richest people, extreme outliers that you can see from a distance. The little red dots are the rest of the population, the ones you need a more sensitive instrument to find, and who actually tell you what the population looks like on average. This perspective has led some researchers to propose that the little red dots might represent a dust-obscured phase through which many or most early massive black holes pass. A phase when the black hole is growing rapidly, surrounded by dense gas and dust that absorbs most of the energetic radiation and re-emits it in the infrared, making the object appear red and compact. Eventually, as the AGN energy output drives away the surrounding gas and dust, a process called blowout, the object transitions into a more typical, less obscured quasar phase. The little red dots in this picture are young, still embedded AGN that haven't yet blown away their cocoons of gas and dust. This evolutionary sequence, from obscured little red dot to revealed quasar, is appealing because it provides a natural mechanism for the transition between different phases of AGN evolution. It also predicts specific observational signatures that can be tested. Objects in the transition phase between little red dot and unobscured quasar should show partial dust removal, perhaps asymmetric dust distributions, or the presence of outflows driven by the AGN feedback. And there are indeed some objects in Webb's data that look like they might be caught in exactly this transition state, with both red dusty components and bluer, less obscured components visible simultaneously. But here again, the V-shaped spectral feature of the little red dots is a problem. In the simple blowout model, you'd expect either a fully obscured red spectrum or a fully unobscured blue spectrum. The fact that some little red dots show both simultaneously, a blue component and a red component at the same time, is not easily accommodated by a simple inside-out dust-clearing model. Something more complex is going on. Chapter 18. Are we looking at the universe forming its spine? Let me take a step back from the technical details for a moment and talk about what this all means at a more cosmic level, because I think there's a perspective on the little red dots that hasn't been fully appreciated in most coverage of this topic, and it's one that I find genuinely profound. The universe we live in today has structure at essentially every scale. Individual stars, star clusters, galaxies, galaxy groups, galaxy clusters, superclusters, filaments and walls of galaxies stretching hundreds of millions of light years, and at the centre of all this structure, at the nexus of every major gravitational node, there is a supermassive black hole. Not sometimes, not usually, always. This is a remarkable fact. Supermassive black holes are not peripheral features of the universe. They're not an interesting footnote in the story of cosmic evolution. They are, in some deep sense, central to the organisation of matter on the larger scales. The most massive galaxies, the ones that anchor the largest clusters, the ones that sit at the intersections of the great cosmic filaments, contain the most massive black holes, and the properties of those black holes are tightly correlated with the properties of their host galaxies, in the way we discussed earlier, suggesting a deep and fundamental connection. The question of how this situation came to be, how the universe went from a relatively smooth, featureless distribution of matter after the Big Bang to this intricately structured cosmos where black holes and galaxies are inextricably linked, is one of the deepest questions in cosmology, and the little red dots might be showing us the answer. If the little red dots are, as many researchers now suspect, the early progenitors of today's massive galaxies and the seeds of today's most massive black holes, if they represent the moment when the gravitational hierarchy of the universe was being established, when the nodes that would eventually become cluster-centering elliptical galaxies were first forming their black holes and their stars in a rapid, compressed burst, then what Webb is showing us is nothing less than the universe constructing its own spine. The little red dots might be the moments of creation of the organising centres around which all subsequent cosmic structure was built. The cosmic infrastructure is being laid down in those tiny, red, impossibly bright pinpricks of light 13 billion years ago. That's a remarkable thought to sit with, and it raises a question that scientists don't yet have a good answer to. What triggered these events? What caused the gas to collect in those specific places at that specific time and begin the simultaneous black hole and galaxy formation process that the little red dots represent? The answer, almost certainly, has to do with the large-scale structure of dark matter. The dark matter halos that formed at the peaks of the primordial density field, the most massive and earliest forming nodes of the cosmic web, would have been the gravitational sinks that attracted the first large collections of baryonic matter, the ordinary gas that eventually formed stars. And the most massive, earliest forming halos would have produced the most extreme environments, the densest gas, the fastest collapse, the most rapid black hole growth, the most intense star formation. In this picture, the locations of the little red dots in the early universe correspond precisely to the locations of the most massive dark matter halos, the places that will, over the next 13 billion years, accrete more matter, undergo more mergers, and eventually become the centres of today's largest galaxy clusters. Webb can't see dark matter directly. Nobody can. But by mapping the distribution of the little red dots across the sky, by studying which ones are near each other and which are isolated, researchers can begin to statistically infer the dark matter environments in which they live. This kind of analysis, comparing the clustering properties of the little red dots with the predictions of models for how dark matter is distributed, is one of the most powerful tests of the theoretical framework. Early results from such analyses are intriguing. The little red dots appear to be more strongly clustered than typical galaxies at the same redshifts. They preferentially live in denser environments, which is consistent with them being the most extreme outcomes of structure formation in the densest regions. This is reassuring from a theoretical standpoint, even as the overall number density of these objects remains a challenge for the models. Chapter 19. The Next Decade. What we'll learn and how. Okay, so where does this all go from here? What are the key observations and analyses that will move the needle on this mystery in the coming years? And what would it take to definitively resolve the major open questions about the little red dots? Let me lay out the scientific roadmap as clearly as I can, because I think this is one of those areas where the path forward is relatively clear even if the destination is not. The most immediately impactful observations will continue to come from Webb itself. The telescope is in excellent health, with fuel reserves that suggest it could operate for 20 years or more, far beyond its nominal 10-year mission. Over the coming years, continued deep field surveys will expand the sample of little red dots from hundreds to thousands, providing the statistical power needed to characterize the population robustly, study how their properties vary with redshift, and identify rare or extreme members that might be especially informative. Particularly valuable will be observations at the longest wavelengths accessible to Webb, using its MIRI instrument, the mid-infrared instrument. MIRI observes at wavelengths from 5 to 28 microns, which at the redshifts of the little red dots corresponds to rest frame near-infrared and optical emission, the wavelengths that are most diagnostic of stellar populations and dust content. MIRI observations are slower and more challenging than NIRCam observations, but the data they provide is invaluable for disentangling the stellar and AGN contributions to the light from these objects. There's also enormous scientific value in X-ray observations of the little red dots. X-rays are a direct probe of AGN activity. Actively accreting black holes are bright X-ray sources. Chandra, the orbiting X-ray observatory, has tried to detect some of the little red dots in X-rays, with mixed results. In some cases, objects with clear broad-line AGN signatures in the optical and infrared are surprisingly faint or even undetected in X-rays, which is itself puzzling. Either there's a lot of material absorbing the X-rays before they escape, extreme Compton thick obscuration, where even X-rays can't get out, or something about the AGN in these objects is producing less X-ray emission than typical. A next-generation X-ray observatory, with substantially greater sensitivity than Chandra, would be transformative here. The proposed mission AXES, or the European Athena mission, if funded and launched, could provide X-ray detections of many little red dots and directly probe the column density of absorbing material along the line of sight. Radio observations with next-generation radio arrays, including the planned Next-Generation Very Large Array, or NGVLA, will be able to detect the faint radio emission from AGN in the little red dots, and also probe the cold molecular gas that fuels both star formation and black hole accretion. Knowing how much molecular gas these objects contain and how it's distributed is crucial for understanding what drives their extreme properties. And then there's gravitational wave astronomy. As black holes in the little red dots merge with each other, and with the black holes in other galaxies over cosmic time, they produce gravitational waves. The planned space-based gravitational wave detector, LISA, the Laser Interferometer Space Antenna, scheduled for launch in the mid-2030s, is specifically designed to detect gravitational waves from massive black hole mergers throughout the universe. If the little red dots really contain the massive black holes implied by their spectra, then LISA should detect gravitational waves from the mergers of black holes in the mass range of millions to billions of solar masses, providing a completely independent line of evidence about the population of massive black holes in the early universe. In fact, LISA might be able to do something extraordinary: detect individual merger events at the redshifts, where the little red dots live, and provide precise masses for the merging black holes. Combined with simultaneous electromagnetic observations of the merger by Webb and other telescopes, this would give us an unprecedentedly detailed picture of what these objects are and how they behave. On the theoretical side, the next generation of cosmological simulations will be instrumental. Simulations are being developed that incorporate more realistic models of AGN feedback, super Eddington accretion, and stellar feedback in the high redshift environment. These simulations are computationally extremely demanding to resolve the small-scale processes happening inside a little red dot, while also simulating a large enough volume of the universe to contain a statistically representative sample of them is a formidable challenge. But computing power is increasing, and algorithmic improvements are making ever more ambitious simulations possible. One particularly interesting approach involves what's called zoom-in simulations, running a large cosmological simulation at relatively low resolution to get the overall structure of the universe, identifying the halos where little red dots are expected to form, and then rerunning those specific regions at much higher resolution with much more detailed physics. This allows a close-up view of the processes inside these extreme early objects without the computational cost of running the entire universe at high resolution. Chapter 20: Rethinking the Cosmic Story. Throughout this video, we've been talking about the little red dots as a problem, as objects that challenge our models, that don't fit, that need explaining, and that framing is accurate in a scientific sense. But I want to end with a different framing, because I think challenges like this are not just problems, they're gifts. Every time observations reveal something that theory didn't predict, every time the universe turns out to be richer and stranger than our models, it's an opportunity. It's an opportunity to learn something genuinely new about how reality works, and those opportunities don't come as often as you might think, because most observations confirm what we already expected. The universe is usually obligingly consistent with our theories. The little red dots are not being obliging, they're being stubborn and weird and magnificently confusing, and that's exactly what you want if you're trying to push the boundaries of knowledge. Think about what we've discussed in this video. Objects at the edge of the observable universe, glowing with the light of 13 billion years ago, that appear to host black holes too massive to have formed in the time available, in galaxies too massive to have built up their stars so quickly, with spectral properties that don't match our standard models of either galaxies or AGN, appearing in numbers that exceed our predictions. Each one of these anomalies is a crack in the wall of our current understanding, and every crack is a potential window into something new. Maybe the resolution will be relatively modest, better models of star formation efficiency and black hole accretion in the early universe, without requiring any fundamental changes to cosmology. That would still be a significant scientific advance, improving our understanding of how galaxies and black holes form and evolve. Maybe the resolution will be more dramatic, a revision to our understanding of dark matter or of inflationary physics that changes the predicted pattern of early structure formation in ways that accommodate the Webb results. That would be a genuinely major development in fundamental physics. Or maybe, and this is the most exciting possibility, even if it's the least likely, the little red dots are pointing towards something genuinely revolutionary. Something that changes not just the details of our models, but the foundational framework of cosmology itself. That would be the rarest kind of scientific discovery, the kind that doesn't just add to knowledge but restructures it. We don't know yet which of these possibilities is correct, and that uncertainty, far from being frustrating, is the very essence of what makes science exciting. We are right now at the beginning of understanding something genuinely new about the universe. Webb has lifted the curtain on the cosmic nursery and found something unexpected in the crib. And now, the real work begins. The little red dots are tiny. They're impossibly faint. They're billions of light years away, and the light we're catching from them left its source before our solar system existed, before the Milky Way had taken its current shape, before most of the stars in the universe had even formed. And yet, in those tiny red smudges there is information, coded in photons that have been travelling since the universe's childhood, that has the potential to rewrite our understanding of the cosmos. That's what Webb is doing. That's what science is doing. Right now, today, with data that's still being collected and analysed and debated, humanity is reaching back to the very dawn of cosmic time and beginning to read the story written there. And the story, it turns out, is stranger and more wonderful than we imagined. Conclusion: the red dots and the bigger picture. So let's bring it all together. The James Webb Space Telescope has identified a population of objects in the early universe, compact, intensely red, surprisingly bright, hosting what appear to be extraordinarily massive black holes that don't fit comfortably within our current understanding of how galaxies and black holes form and evolve. These little red dots appear in significant numbers at redshifts between roughly 4 and 10, corresponding to the universe's first 1.5 billion years, and their properties collectively challenge some of the most basic predictions of our standard model of cosmology and galaxy formation. They're too massive, appearing in too great numbers, too early. Their black holes are too large relative to their host galaxies. Their spectral properties are weird in ways that standard models of AGN and star formation struggle to reproduce. Their compactness implies physical conditions that are extreme, even by the standards of the extreme earlies. universe. The leading hypotheses for what they are include dust-obscured AGN, feeding black holes surrounded by thick cocoons of gas and dust, caught in a transitional phase before they blow out their surroundings and reveal themselves as unobscured quasars. They might be compact starbursts with massive black holes growing simultaneously in a period of coevolution that our models don't fully capture. They might be marking the sites of the most massive dark matter halos in the early universe, the seeds of today's galaxy clusters. Or they might be pointing toward physics we haven't fully incorporated into our models, super Eddington accretion, new dark matter properties, modifications to inflationary predictions, or something else entirely. What we know for certain is that they're real. The spectroscopic confirmations are solid, the broad emission lines are real, the high redshifts are real, the extreme properties are real. These objects exist and they are a genuine challenge to our current framework. What we also know is that this story is far from over. Webb continues to observe. New data arrives constantly. Theorists are working hard to build models that can accommodate what we're seeing. New observatories, LISA, the next generation X-ray telescopes, the extremely large ground-based telescopes, the NGVLA, will provide new lines of evidence in the coming years. The picture will clarify. Some of the current confusion will resolve into understanding, and almost certainly some new surprises will emerge. Because that's what always happens when you build a better telescope and point it somewhere new. The universe rewards you with wonders you didn't expect, and the little red dots, strange and perplexing as they are exactly that kind of wonder. A signal from the deep past that the cosmos is more inventive, more extreme and more fascinating than we give it credit for. The dots are red. The mystery is deep, and the greatest telescope humanity has ever built is staring at them, collecting photon by precious photon, slowly bringing the answer into focus. Stay tuned. This story is just getting started.